Okay, so as we get started with this idea of taking a limit as we go towards either positive or negative infinity, we've got some rules here as they relate to rational functions. And fortunately for you, these are all golden oldies from pre-calc that you remember. So let's begin with this big box here, and it says if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is going to be 0. It's sort of like the function is bottom heavy, so to speak. And if the degree of the numerator is equal to the degree of the denominator, then the limit is going to be the quotient of leading coefficients. And you'll probably remember doing that once we hit the example here in a second. Okay, and if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. Alternatively, you could say it goes to infinity or negative infinity depending upon the end behavior of the function. So as we've discovered, when it comes to a limit at infinity, this is nothing more than the end behavior of the function itself. Okay? And rational functions always approach the same horizontal asymptote to the right and to the left. However, functions that aren't rational may approach different horizontal asymptotes to the right and the left. And as we talk about that, you'll sort of see what's going on here. And now one of the tools that you're going to need to be able to do for this particular idea of a limit at infinity is to come up with an end behavior model. Okay, now you're probably wondering what exactly is this end behavior model. It is a function that behaves in exactly the same way as your larger function, and it allows you to be able to determine what the limit at infinity is maybe a little bit easier. So this is kind of an alternate method to maybe finding the horizontal asymptotes or those three little golden oldies that we talked about on the previous panel. So if I want to find an end behavior model, what it is it's what's called a power function. So you might see those words used to describe an end behavior model, a power function end behavior model. And what is a power function? Well, a power function is just simply a one-term function that has an exponent on x of some kind. Now, to find these end behavior models, it is super, super easy to do. All you need to do is take the leading coefficients and divide them, and that's going to be your end behavior model. Okay, so let's start with this first one right here in A, and the leading coefficient or the leading term upstairs is a 2x, and the leading term downstairs is a 3x squared. So what I'm going to do is I'm going to take that 2x over 3x squared, and I'm going to reduce it down, and when I cut down that power of x, my model is 2 over 3x. So I want you to think about for a second, what's the behavior as I go to positive infinity? Well, as x gets super large, this function is going to go to 0. Now, if you remember, since this is bottom heavy, the original function has the same end behavior. It too will go all the way to 0. So let's do this for the other two real quick, and you can see how it works just as easily here. In the case of question B, they have the same degree, so we know that the end behavior comes from dividing the leading coefficients. So the end behavior is going to come from taking 2x squared over 3x squared, and again, when we reduce all the way down, we get 2/3. So my end behavior model is 2/3, and not surprisingly, that too is our horizontal asymptote if we use those guidelines. So this power function end behavior model is going to be just another vehicle for you to get to the the horizontal asymptotes quickly. Okay, so for part C, top heavy here as we notice, and the end behavior model comes from taking the leading terms and reducing them down. So it's going to be 2x over 3. Now, as we all know, that's like saying a line that has a slope of 2/3 and a y-intercept of 0. So its end behavior as we go to positive infinity is also going to be positive infinity. It's going to get infinitely large. And that is going to give us the opportunity we need to be able to say that the end behavior model is 2x over 3. All right, good idea. Let's move on. Okay, so if r is a positive rational number and c is any real number, then what we are looking for here is we are looking for the limit as x goes to infinity of some c over x to the r power. Well, honestly, that is going to be any real number. I think we got to be careful there on the r, but r is a positive rational. Okay, that's good. We're going to end up with 0 is what it boils down to. And we're going to end up with 0 there as well. Now, we've got an interesting case here in this example 1 where it says something to the effect of use graphs and tables to determine the asymptotes. So what I want you to do is I want you to go ahead and pause this video, and I want you to take a moment and graph this function. Okay, now, I know I said pause the video already, but if you're still listening by now, you want to make sure that if you're using your TI calculator, you type this in as y1 is equal to x in parentheses over another set of parentheses and the square root of x squared plus 1. Okay, so that's how it should really look like in your calculator. I'm going to hit the pause button here, and we're going to come back to this in just a moment once we see the graph. Okay, so as we come back here, this is a Desmos picture of that particular graph, and you will notice that this is that rare case where we do have two horizontal asymptotes, so the limit as x approaches infinity of our function looks to be 1, and the limit as x approaches negative infinity of our function looks to be -1. So that's that rare case right there. So hopefully you were able to take a look at that and observe that for yourself. Okay, now lastly we want to get into this definition of a vertical asymptote, and it's actually not too bad to do. I mean, we sort of know what vertical asymptotes look like. You think about something like the tangent function, our dear friend the tangent function. And that function has a lot of vertical asymptotes, like pi over 2 and 3 pi over 2 and so on and so forth. Okay, so here's the true definition of a vertical asymptote. And if it looks a little bit like the definition of a horizontal asymptote, you're not wrong here. Okay, so the line x is equal to a is a vertical asymptote of the graph of the function if either the limit as x approaches a of your function is infinity, or the limit as x approaches a from your function is negative infinity. Now, I have to say that this is probably more of like a one-sided limit situation, where if you are approaching from one side or another, then that's going to let you be able to find that. Alright, so what I would encourage you to do is once again pause the video one more time and go ahead and graph the function that you see in part B down there. Let's see if we can find those vertical asymptotes. Well, quite honestly, let's do that part first. And you're going to find out that this factors into +2 and -2 in a hurry. So the vertical asymptotes are located at x is equal to -2 and x is equal to +2. Hopefully that's something that didn't really cause you too much grief. So now that you know that, see if you can find what the behavior is as we approach -2 and +2 from the left and from the right. So let's pause the video here again and go investigate for yourself and be ready to come back to this in a second. All right, so you see my answers there. As we approach -2 from the left, you should be going to positive infinity. As we approach -2 from the right, you should be going to negative infinity. as you go from towards 2 from the left, negative infinity, going down, and 2 from the right, positive infinity. Okay, folks, that's what I've got here, and that's our lesson on limits at infinity.